Let us take today some of the problems on materials and heat balance in roasting. So, what I planned, first of all, I will project all the problems in the form of the slide to you. I will read out the problem, so that you can understand and you have enough time to think, and then I will proceed to solve the problems. So, here we go with the problem number 1. The problem number 1 states roasting is an unit process in which sulphide is converted to oxide partially or fully. That is what we have seen in the roasting. In production of copper from chalcopyrite, partial roasting is carried out. Production of copper from chalcopyrite, there is always partial roasting is done. That means, it is not deadly roasted. Now, the problem is as follows. In one roasting unit, an ore concentrate of the composition 21% Cu2S, 40% FeS2, 31% SiO2 and 8% H2O is roasted using air. You need an oxidizing medium, and oxygen from air is derived from air and used as an oxidizing medium. The roasting unit is heated by fuel oil of composition 85% carbon and 15% hydrogen. The amount of oil is 5.2% of the weight of the ore. Air for combustion and roasting is 110% in excess of the theoretical requirement. Now, as I have said, the excess air can be given in two ways. Either I say 210% of the theoretical air, or I say 110% of the excess air. So, whichever way, one should be clear how much amount of excess air is used. So, in this particular problem, the air for combustion and roasting, that is both combined, the requirement of air for combustion and roasting is given, which is 110% in excess of the theoretical requirement for both combustion as well as roasting. The gases from combustion and roasting mix together, because when combustion and roasting they occur simultaneously in a reactor, then the gases which are generated, they mix together and are carried off through a flue. Flue means a passage through which the gases are carried out of the reactor. Now, sulphur passes as sulphur dioxide, that means there is no formation of sulphur trioxide. That is what the problem says. The roasted product consists of CuO, Fe2O3 and SiO2. Calculate A, weight of roasted product, B, cubic meter of air at 1 atmosphere and 273 Kelvin, and second at 1 atmosphere and 973 Kelvin. This is I have given just to illustrate the volume of air that will be in a reactor, because you are carrying out the roasting at high temperature. Third, amount of H2O per cubic meter of flue gas. This is the problem number 1. Now, let us go to the problem number 2. Problem number 2 states the flue gas in one particular roaster analyzes, say the analysis is given on volume percent. Now, wherever if I have not given the analysis of gas and I have not written say volume percent, then the analysis of gases is always given on volume percent unless otherwise stated. If it is stated, it is fine, but if it is not stated, then you have to take that the volume of gases they are given as volume percent, whereas the percentage composition of solid, it is given on weight percent, needless to mention. So, the flue gas in one particular roaster analyzes CO2 2%, SO2 7.4%, H2O 0.6%, nitrogen 80% and oxygen 10%. The ore concentrate analyzes 10% copper, 34% iron, 15% SiO2 and 41% sulphur. During roasting, 80% of sulphur is removed. The fuel is coal containing 75% carbon. The ore and fuel are separate, but the resulting gases mix. Now, what this means is that you are supplying through different inlets the required amount of ore and required amount of fuel, but then the gases which are produced as a result of roasting and combustion, they mix together and the together volume, it is discharged from the reactor. Now, you have to calculate the following: amount of roasted product assuming it to contain Cu2s, FES, Fe2O3 and SiO2, because this particular statement it has to be given, otherwise there could be different products, roasting product can form. So, one has to specify what type of roasted product we are looking for in a particular problem. So, this particular problem states that you have to calculate the amount of roasted product assuming it to contain whatever is written over here. B, the cubic meter of flue gases. Now, this cubic meter of flue gases is very important in order to design the flow passage, because that much amount of flue gas must flow out of the reactor. C, amount of fuel used. D, percent excess air used for combustion and roasting. E, theoretical ratio of air required for roasting to combustion. So, this is what problem 2. I hope you must be able to grasp the problem and understand the problem before we proceed to solve them. Problem number 3, a zinc concentrate of composition zinc sulphide 76%, lead sulphide 7%, FeS2 7% and rest inert is roasted continuously with dry air. Assume zinc sulphide converts to ZnO, PbS to PbO and FeS2 to Fe3O4 and all sulfur to SO2 and SO3. Now, while solving the problem, this condition of roasting must be kept in mind, because it is only through these conditions you can calculate the amount of roasted product. So, accordingly you have to assume or you have to consider the formation of the following products under the following condition. That means, ZnS converts to ZnO, PbS to PbO, FeS2 to Fe3O4 and all sulfur to SO2 and SO3. You cannot take it that all sulfur is going to SO2 while solving the problem, because the problem says the sulfur is converted to SO2 and SO3 both. That is an important thing. The gases leaving the system analyzes 7% SO2 and 2.5% SO3 on volume basis. Calculate A, rate of blowing of air in meter cube per minute when 100 ton concentrate is roasted in 24 hours. B, excess air, of course, excess air in percent, or you can report fraction also, it does not matter. C, analysis of flue gases, and D, perform heat balance of the roasting per ton of concentrate when reactants enter at 298 Kelvin, the products leave at 1100 Kelvin and roasting is carried out at 1100 Kelvin. That means, whatever the temperature of the roasting, the products they leave at 1100 Kelvin. Now, here the products consist of roast product as well as gases. So, both the products are leaving at 1100 Kelvin and the reactants enter at 298 Kelvin. Problem number 4 is also on the heat balance. Now, in a multiple hearth roaster, copper concentrate of composition chalcopyrite, which is CuFeS2 33%, Cu2s which is chalcocite is 7%, FeS2 34%, SiO2 19% and moisture 7% is roasted. Now, multiple hearth roaster is a typical roasting reactor for chalcopyrite concentrate. It consists of several hearths and material from one hearth fall into other hearth before the roast product discharge the other end of the roaster. Now, here the problem says all iron is oxidized to Fe2O3. This condition you have to keep in mind, and 50% of copper oxidizes to CuO and rest to Cu2s. The furnace gases analyzes 12% oxygen and leaving the furnace at 900 Kelvin. The roast product is also discharged at 900 Kelvin. Reactants enter at 298 Kelvin. No fuel is used. Here we are not using any fuel in this particular problem. However, in a particular problem the fuel can be used and accordingly it can be considered. What you have to calculate? Weight of roasted product per ton of concentrate, percent sulfur in the roast product and express it as percent of original sulfur. C, volume of air and excess air. D, composition of the gases, and E, heat balance of the process. So, these two problem 3 and 4, they are given to train you in the heat balance aspect of the roasting. I hope you must be remembering the heat balance, heat input to be calculated and heat output is to be calculated, both has to be balanced and to see whether heat deficit is there or heat excess is there. So, that is what the objective of the roasting. Problem 5th, zinc concentrates of a location are composed of 60% zinc present as ZnS, iron present as FeS, mind you not FeS2, and 7% SiO2. On roasting, zinc oxidizes to ZnO, iron to Fe2O3 and sulfur to SO2. 3% of zinc sulphide however remains unoxidized. Please keep in mind while solving the problem, 3% of zinc sulphide remains unoxidized or unchanged, whichever way you want to say. Coal equal to 20% of raw ore is used. The ashes from the coal do not mix with the ore, but the products of combustion pass through the furnace and into the flue, mix with the gases from the roasting. Now, the ashes generally means ash plus percentage carbon. So, what the problem says that you are not to bother, I mean you may think that the ash will form where it will go. So, the problem simply says the ashes from the coal do not mix, they remain in the reactor or somewhere else, but the products of combustion pass through the furnace and into the flue, mix with the gases from the roasting. The coal is 72% carbon, 6% hydrogen, 8% oxygen, 2% sulfur and 12% ash. What is said is here that with the ash content you need not bother, because whatever ash it is falling into the reactor, it is not being carried away by the products of roasting as well as combustion. The flue gases carry 12% oxygen. Want you to calculate the weight of roasted ore and the percent as sulfur in the roasted ore, the theoretical volume of air used in roasting and for combustion of coal. Remember, it is said theoretical volume of air. What is meant by theoretical volume of air? That means, you will be writing down the stoichiometric reactions, that is balanced chemical reaction, and then from the balanced chemical equation you will be calculating whatever is required to calculate. C, the percent composition of the flue gases and the percent excess air used above the theoretical requirement for roasting and combustion. So, you have to calculate the C also where some amount of thinking is required. Problem 6, galena concentrates are composed of lead sulphide, FeS2 and SiO2. The moist concentrate contain 8% H2O, 28% SiO2 and 11% sulfur. They are roasted down to 4% sulfur. The roasted ore are being composed of FeS, PbS and PbO and SiO2. The last two combined as a silicate. The furnace is fired with coal containing 72% carbon, 4% hydrogen, 8% oxygen, 3% H2O and 13% ash. Needless to say again, ash does not mix with the products of roasting or combustion, because ash is a solid product and it just falls down. The furnace gas analyzed dry are 3% SO2 and 3.5% CO2, 10% O2. Neglect moisture of the air. Calculate per ton of moist concentrate A, the weight of roasted ore. You can call weight of roasted ore or weight of roasted product, they all convey the same meaning, or even sometimes weight of calcine, that is also a term used for roasted product. B, the volume of furnace gases including moisture. C, the weight of coal used. The seventh problem, the lead concentrate of a particular plant analyzes PbS 83.1%, FeS 7.9%, SiO2 3% and remaining is calcium carbonate. The concentrate is treated by roast reaction method to produce lead. Now, there is earlier used in the method which is called roast reaction. The roasting is followed by a reaction to produce lead. The reaction during roasting stages are 2 PBS plus 3 O2, that is equal to 2 PBO plus 2 SO2, PBS plus 2 O2 equals PbSO4, and 4 FES plus 7 O2, that is equal to 2 Fe2O3 plus 4 SO2. At the end of the roasting stage, all FES is oxidized, but some PBS remains. The formation of PbSO4 and PbO is in the ratio 1:3 by weight. During the reaction stage, following reactions occur: PBS plus 2 PbO, that is equal to 3 Pb plus SO2, and PBS plus PbSO4, that is equal to 2 Pb plus 2 SO2. Both of the above reaction continues till all Pb sulphide, PbO, PbSO4 has been consumed. Now, here in order to solve the problem, you have to read between the lines, and you have to be very careful while understanding whatever said in the problem, because the solving trick, the problem solving trick or the key to solve the problem is inherent in the statement of the problem, provided you read the problem carefully and you understand in between the lines. That is important. Find A, weight of the ore at the end of the roasting stage and its proximate analysis per 1000 kg concentrate. Now, approximate analysis, as I said earlier also, that means you have to find out the analysis in terms of minerals, because when the solid product you have, there is no free sulfur or free oxygen or whatever is there. So, you have to find out the percentage of minerals. D, percentage sulfur eliminated at the end of roasting stage. C, gases formed during A, roasting stage. B, reaction stage in meter cube at 1 atmosphere and 273 Kelvin. So, this is the 7th and I believe it is the last problem, and the next slide as usual, it gives you the data on material and heat balance in roasting, because you may be requiring several data in order to do the heat balance. You may find some data are more or some data are less, but they are all the data are given over here. For example, the formation of zinc oxide, lead oxide, Fe3O4, SO2, SO3, CuO, Fe2O3 and Cu2S, they are all given in terms of delta HR. The respective values are shown and given to you. So, you may use those values in order to the heat balance. At the same time, what has been done over here, the products of roasting as well as gases, that means product, roast product and the gases, their heat content is given at the temperature at which they are living. Otherwise, you could have solved by using the Cp value of ZNO, Cp of PbO, Cp of Fe3O4, Cp of SO2, Cp of SO3, appropriate integrate from 298 to the temperature at which they are discharging, and you get the heat content. So, here instead of that, just to illustrate the problem, because if I do that problem by taking Cp into consideration, it will take a very long time to me. That is why I have selected the path to give you the directly heat content, because the objective is to illustrate the heat balance. However, it is quite possible that if the product live in between temperature, for example, 1150 degree Kelvin, then you have to integrate from 298 to 1150 and get the value of heat content. So, here just to cut short, I have given directly you the value of say heat content at the temperature of the discharge of roast product as well as gaseous product. So, these values are given, so ZNO, PbO, Fe3O4, SO2 and SO3, and next all values are given. Say here also you will find the various values of again the product which are being discharged, or the for example, zinc, lead, iron, sulfur, oxygen, nitrogen, H2O, all values you will find they are given over here. So, as and where you require to solve the problem, you can take these values, or if you want to do further good practice, what I will suggest you go to the standard book, the reference I am giving you after this, and get the value of Cp. Integrate the Cp value from 298 to the respective temperature of discharge of the product and get the heat content in that. That is also the most correct way to do that. So, the last slides give you the answers, which I believe you will not be seeing before you solve the problem, and the last slide it gives you the references which you can use to find out the data, or if you want more data, or if some data I have missed, which I do not think I missed any data, you can see the data from these particular books, particularly the book of I. K. Rao. It also gives you data of CP and H. F. Hine and G. H. Geiger. These two books you can consult for the data. Now, what I have thought, I will go one by one and discuss these problems, and wherever I feel the need, I will solve the whole problem for you. So, here let us see the problem number 1. Now, the problem number 1 says, say you are given the composition of the concentrate and the roasted product which are to be formed. So, if I just illustrate in the form of a block diagram, so this goes this way. That means, here let me take the basis as 1000 kg, 1000 kg ore concentrate, 1000 kg ore concentrate. Now, I am directly writing say Cu2s, FeS2, SiO2 and H2O. So, Cu2s is given 210 kg, 400 kg, 310 kg and 80 kg, that is what given, and plus the problem also says that fuel oil is used and fuel oil composition is 85% carbon and 15% hydrogen. Its amount is 52 kg. Its amount is 52 kg, and the roasted product, the problem says that the roasted product contains CuO, Fe2O3 and SiO2. Now, by seeing the roasting process and the various elements that are involved, one can see that the flue gases will comprise of CO2, N2, oxygen, you have SO2 and H2O. That is what the problem says. Now, you have to find out the roasted product. What will I do? I have to just write down the stoichiometric equation. For example, if I see say Cu2s plus 2O2, that is equal to 2 CuO plus SO2 and 2 FeS2 plus 5.5 O2, that is equal to Fe2O3 plus 4 SO2. Now, let me tell you that the atomic weight which I am using in this problem, for copper it is 64, for iron I will be using 56, for silicon though you may not be needing, but still 28, sulfur 32 and oxygen as 16. These are the atomic weights that I will be using to solve this problem. Now, so straight away you can convert into mole or whichever you, I am writing down straight away because this is very simple. So, CuO, that comes 210 kg, Fe2O3, that is equal to 266.7 kg, and now always remember, because roasting is an oxidation process, if the ore concentrate contains SiO2, Al2O3 or calcium oxide or whatever these type of oxide, they will be transferred as it is into the roasted product, because they have no opportunity to react anywhere, they neither oxidize, at the most they can combine here and there. So, as such the SiO2 of the ore concentrate will directly go to the roasted product. So, it will be 310 kg. So, the total of roasted product, that is equal to 786.7 kg, and this is what the required in the answer. So, we have to calculate now cubic meter of air that is required for roasting and combustion. Well, it is straightforward. The chemical equations I had already written, and according to stoichiometric equation, if you look, you can straight away calculate the moles of oxygen for roasting. Similarly, you can write down the combustion equation, that is the combustion equation, it contains carbon and hydrogen. So, C plus O2 is equal to CO2 and H2 plus half O2 is equal to H2O. So, I will leave this exercise to you, so that you should be able to do it. So, what I will be getting now, say total moles of oxygen, total moles of oxygen required for combustion and roasting, I am writing this. So, the total moles that will be 17.42 moles, rather I will say kg moles, called kg moles. So, mind you, these are the theoretical, I put it theoretical. So, from here we can calculate the theoretical air, that will be equal to 1858 meter cube at 1 atmosphere and 273 Kelvin. Now, the problem says cubic meter of air, and also it says that you are using some 110% air. So, if you want to calculate total amount of air, you cannot calculate unless you calculate the theoretical amount of air. That was the need of calculation of theoretical amount of air, because it is 110% excess air. So, that means 210% of the theoretical air. So, now the actual amount of air which the problem wants to know, actual amount of air, that will be equal to 3902 meter cube, of course, at 1 atm and 273 Kelvin. Now, 1 atmospheric pressure and 270. That is the answer for the problem 1 part B. Now, the part C, it says amount of H2O per cubic meter of flue gas. Now, without calculating the amount of flue gas, you cannot calculate the amount of H2O that is present. So, this also I will leave exercise on you. I will just write down the flue gas that will comprises of CO2, N2, O2, H2O and OSO2, all that you can calculate. The necessary informations are already given in kg moles, that will be 3.68, nitrogen 138, oxygen 19.16. Now, remember this is the excess oxygen, because theoretical oxygen will not be appearing in the gases, it will be utilized for the roasting and combustion, only the excess oxygen will appear in the flue gases. So, H2O is 8.34 and SO2 is 8. So, if you sum total it, then it will be 177.18 kg moles. Now, we have to calculate the amount of H2O per cubic meter of the gas. So, you have to multiply by 22.4 and accordingly you will get the answer. So, the answer is 0.038 kg H2O per meter cube of flue gas. So, let us go to the problem number 2. Now, the problem number 2 is that the flue gas in one particular roaster analysis, the analysis is given. So, here Let me again illustrate a material balance box. So, here the flue gas analysis is given. Flue gas is analyzing CO2, SO2, H2O, N2 and O2. Now, CO2 is given 2%, SO2 is 7.4%, H2O 0.6%, nitrogen is 80% and oxygen is 10%. Now, also the problem says the concentrate is analyzing 10% copper, 34% iron, 15% SiO2 and 41% sulfur. Let us get the basis. So, basis is again 1000 kg ore concentrate. Now, first of all you have to calculate amount of roast product. So, let us calculate first amount of roast product. Now, remember for this calculation you have to read the problem in between the lines, because there are several conditions are given. So, first of all the SiO2 which is 150 kg, all SiO2 will enter into the roast product. Now, about sulfur some conditions are given. So, you can say first of all sulfur oxidized to SO2, that is equal to 328 kg. Therefore, 82 kg of sulfur is in roast product according to the problem, is in the roast product because of the statement which is given in the problem. Now, since 82 kg of sulfur is in the roast product, so from here we can find out amount of Cu2s. Amount of Cu2s, because the roast product will contain Cu2s. So, amount of Cu2s, that will be 160 upon 128 into 100, 100 kg is the copper. So, amount of Cu2s, that is equal to 125 kg. Now, you have to find out sulfur in Cu2s. After finding out sulfur in Cu2s, you will to find out sulfur with FeS. So, sulfur in Cu2s, that will be 25 kg. Then sulfur with FeS, 82 kg of sulfur is in the roast product, 82 minus 25, that is equal to 57 kg. So, this sulfur will be in the form of FeS. So, the amount of FeS, that is equal to 57 upon 32 into 88, that will be equal to 156.75 kg. This is the amount of FeS, this is the amount of Cu2s. Now, iron is as Fe2O3. So, we have to find out now how much iron is left over, so that it can form Fe2O3. So, for that iron in FeS, to find out, that will be 99.75 kg. So, iron with Fe2O3, to find now iron with Fe2O3, how will you find out? You know the total iron which is 340 kg. If you subtract this 99.75 kg, so this iron has to go as Fe2O3. So, iron with Fe2O3, that will be 340 minus 99.75. So, that makes 240.25 kg, that iron that will go as Fe2O3. So, amount of Fe2O3, that will be equal to 343.2 kg. That means, all that you have to multiply by the molecular weight of Fe2O3 and so on. So, this is the amount of Fe2O3 that will be in the roast product. So, now we have calculated all the amounts. So, the amount of roast product, you have to sum total all the roast product Fe2O3, Cu2s, FES and SiO2. So, that will be equal to 774.95 kg, and that is the answer for this particular part. Now, next we have to calculate cubic meter of flue gases. Now, for this you have to do sulfur balance, that is sulfur balance is sulfur in feed, that is equal to sulfur in flue gas plus sulfur in roast product. So, if you do this balance, then the amount of flue gas that you can do yourself this balance, that comes out to be equal to 138.51 kg moles, because you assume x is the amount of flue gas and accordingly you can proceed with the balance. So, this will be equal to 3102.7 meter cube at 1 atm and 273 Kelvin. Now, next you have to find out amount of fuel. So, next you have to find out amount of fuel. How will you find out amount of fuel? In that you calculate the amount of CO2, because the CO2 is solely coming from combustion of carbon of the fuel. So, from that you can find out. So, the amount of fuel, I am straight away writing the answer. I leave it on you. Amount of fuel, that will be equal to 44.32 kg. All that you have to find out CO2 and do with the carbon balance, and you can find out. Now, D part, now this is the answer, and this is the answer for B part. Now, the D part you have to calculate percent excess air. Now, in calculating percent excess air, first of all you calculate the total amount of air, that is you do with nitrogen balance. Say nitrogen in air, that is equal to nitrogen in flue gas. So, if you do that balance, then it comes the nitrogen in air, it comes 110.808 kg moles. Now, you can find out oxygen in air. This is the actual amount of oxygen which is being used, that will be 29.47 kg moles. Now, this is the total amount of oxygen which is supplied. Now, in order to know the excess, what you have to do? You have to find out the theoretical amount of air. Now, the theoretical amount of air consists of combustion of sulfur to SO2, carbon to CO2, then Fe to Fe2O3 and H2 to H2. Now, mind you, this H is from the fuel. So, if you calculate all, that will be give you the theoretical oxygen. If you do this calculation, then you will get theoretical oxygen, and this theoretical oxygen, that will come out to be equal to 16.653 kg moles. So, now the excess air will be, would be, you have to divide both, that will be around 77%, that will be the excess air, and you have to calculate the ratio of theoretical air. The ratio of theoretical air for roasting upon combustion This you can do yourself, I leave it on you. This ratio will come out to be equal to 4.23. So, that is what the problem number 2. Now, I illustrate straight away in this sequence of material balance the problem number 7. Now, the problem number 7 is typically a so called roast reaction method to produce lead. Lead concentrate analysis is given and roasting and reaction stages equations are given and further conditions are given. So, let us consider 1000 kg lead concentrate, 1000 kg lead concentrate. Now, again I am telling you this problem needs very careful reading in between the lines, that is very important. So, I can write here PBS, FES, SiO2 and calcium carbonate. PBS 831, that is in kg, here I am writing kg moles, FES 79, 30 and 60, kg moles 3.477, 0.898, 0.5 and 0.6. Now, the roasting stage reactions are given and reaction stage equations are given. Now, the problem says following. The problem says following: first, end of roasting state, end of roasting stage, all FES is oxidized, all FES is oxidized. Second, it says all PBS is not oxidized, all PBS is not oxidized, that is what the problem says. Third, it says that the PbSO4 is to PBS, the ratio is 1:3 by weight, that is what the problem says. Fourth, it says that the reactions at the roasting at the reaction stage continues till all PBS, PBO and PbSO4 is consumed. So, the reaction at the reaction stage continue till all PBS, PBO and PbSO4 has been consumed. Now, this is all given in the problem, I am writing so that you understand. Now, again fifth, the problem says all PBS is reduced to lead by reaction stage, that is the fifth, all PBS is reduced to PB by the equations which have been written under the reaction stage. So, now I proceed, say roasted ore will contain PBS, PBO, SiO2, CaO, Fe2O3 and PbSO4. Now, say I can calculate now straight away Fe2O3, that will be equal to 71.8 kg, you can calculate, there is no problem. Calcium oxide will go as it is 33 kg. Now, SiO2, that is equal to 30 kg. So, we know here SiO2, we know calcium oxide, we know Fe2O3, but the calculation of PBS, PBO and PbSO4 requires a careful thinking, because both reactions now you have to consider. So, let us consider now, let x kg PbSO4, which means 3 kg, 3x kg is PBO at the roasting stage. That is what given in the problem. Now, let us say let y kg PBS left at the end of roasting stage, at the end of roasting stage. Now, what will I do now? Now, you have to do material balance of lead. You have to do now say material balance, you have to do now say material balance of lead to do in both these stages, in the roasting stage as well as in the reaction stage. So, material balance of lead in roasting stage. In roasting stage, mind you, we are doing material balance of lead. So, material balance of lead in the roasting stage is x upon 303 plus 3x upon 223 plus y upon 239, that is equal to 831 upon 239, that is equation 1. Now, this equation, remember, it has been done on the lead balance. This x upon 303 is for PbSO4, this is PbO, this is lead sulphide, and this is what the total lead in the charge 1. So, material balance of lead in reaction stage that is equal to 3x upon 446 plus x upon 303, that is equal to y upon 239, and this is equation 2. Now, if you solve both the equations simultaneously, then you will get the value of x and y. Now, these two are the important thing, these two equations which I have found for you, that you can also form, provided you read the statement of the problem very clearly and you understand what is given in the problem very clearly. Otherwise, you may get some difficulties. Now, we have one equation 1 and 2. Now, we can solve those equations. So, if I solve this equation, then x that comes out to be equal to 130 kg. This is the weight of PbSO4. Y that is equal to 311 kg. This is PbS left, and PbO, that is 3:1, that is 3 into 130, that is equal to 390 kg. So, what we have to do now? Now, we have to write down say weight of ore after roasting, weight of ore at the end of roasting, that is what the problem says, at the end of roasting. So, we can write down now Fe2O3, CaO, SiO2, PbSO4, PbO and PbS. So, Kg, that is 71.8, 33.0, 30.0, 130.0, 390.0 and 311.0. So, total will be 965.8 kg. Well, if you want percentage, So, in terms of percentage 7.4, 3.4, 3.1, 13.5, 40.4 and 32.2. That is what the answer. Now, the B part says percentage sulfur eliminated at the end of roasting stage. So, you know how to calculate sulfur which was there earlier and now how much it is eliminated, whatever is there in the roasting ore that you have to subtract it. So, percentage sulfur eliminated as asked in the problem, that is equal to 60.5%. This is the sulfur. Now, the gases formed during the roasting stage and during the reaction stage Now, during resting stage, the gases formed that is equal to 72.8 meter cube, and the reaction stage it is 38.8 meter cube. Now, as regard percent sulfur eliminated, you can also calculate percent PBS, which remains unchanged at the end of roasting stage. At the end of roasting stage, that you can also calculate, it will come out to be equal to 37.4%. So, this is what the solution from problem 7, but I appeal to all of you that please attempt the problem yourself before looking into the solution of the problem.